Hello, I'm Ivan Fedyanin, I'm software architect, and in this video we continue our series of videos about consistency models achievable with leader-follower replication. Those videos are based on my article published on my website fedyanin.com, and here it is on the screen. So in previous two videos we have covered this part. We covered some intricacies of implementation of real leader-follower systems like Postgres, MySQL, MariaDB, and how they can affect what consistency models we can achieve, because there are some implementation details which are tricky and they are not obvious at first glance. And in the second video, we have covered what eventual consistency is, how to achieve it, and some example of real system and some problems which we can have and how can we solve them. And in this video, we will cover next section of the article related to several consistency models and how we can achieve them with leader-follower systems. We will cover consistent prefix reads, session guarantees, also known as client-centered consistency models, causal consistency, and sequential consistency. And everywhere where is applicable, I'll give an examples and provide some potential real systems where we could use those consistency models. So let's start. Consistent prefix read is very simple for understanding, and it basically means that client must always on each read see the state of the data exactly as they were in some point in time in leader. So for example, it's possible that client will see some fresh state of the system, and on the next read it could potentially see some older state of the system, kind of get back into the past. But the requirement that those both states, old and new, that they really existed. So it prohibits some non-existing states. It can be very well illustrated by this picture which we see on the screen. So we see that leader and asynchronous follower nodes, and the leader has some log of writes. And here we just have all writes numbered from 1 to 7, and follower has a replicated portion of those writes, which is called consistent prefix. It's called consistent prefix because we see here writes 1, 2, and 3, and we see that on leader at some point in time there existed writes 1, 2, and 3. And this portion just was not replicated yet, but when it will be replicated, we'll just build up this consistent prefix more and more. And it seems that leader-follower replication kind of perfectly fits this consistent prefix reads model, because we have leader and follower and we have some kind of replication log, and this log is replicated just one by one, write by write, and it's one by one applied on follower. So it seems initially that consistent prefix read is very easily achievable in leader-follower system, and it's really so. There is just one small consideration, that out-of-order writes must be prohibited in such leader-follower system. So, for example, we must be sure that if we have writes 1, 2, and 3, then they must appear on follower in exactly the same order. So first there should be write 1, then 2, and then 3. We can't imagine situation, for example, when we have writes 1, 2, and 4, because it wouldn't be consistent prefix read. And assuming that we don't have out-of-order writes, then this requirement is achieved in any mode of usage of leader-follower system. Indeed, we could read from leader, we could read from asynchronous followers. Of course, we can read from synchronous followers. Moreover, we can read from random follower. So we can read from one follower, later we could read from another follower, and we still will get the consistent prefix under the condition that out-of-order writes are prohibited. In previous video, we have discussed in details what are the reasons for out-of-order writes, but let's just remind here very briefly. The reason for out-of-order writes is concurrency and parallelism in some way. For example, let's see example of asynchronous followers and multi-threaded replication. And we see that there are multiple writes, multiple clients who write constantly on leader. Leader is a single machine and it arranges all writes into some total order. But then, due to performance reasons, they might be replicated in multiple threads to asynchronous follower, and they can be applied in slightly different order. And that's the reason for how they can appear with asynchronous followers. Also, they can appear with synchronous followers because sometimes a synchronous process it's not end-to-end from write to when this write will be visible on a follower. For example, in MySQL with the semi-synchronous mode, we have one synchronous follower, but the synchronous process is only applicable to the delivery of messages of this binary log from leader to synchronous follower. But then this binary log still could be applied in parallel, and clients will see some data not when they just arrived to binary log, but when this binary log is applied and it becomes visible. So those are the reasons for out-of-order writes. Of course, on almost any system, we can prohibit them, and there are special parameters for that. And those parameters are not always by default in such a mode which prohibits them. So let's get back to our consistent prefix read. And now we know that if out-of-order writes are prohibited, then whatever mode we use as a system, we can read from any follower or leader. We could randomly switch from one follower to another, and we will get consistent prefix reads. Let's see a real system where we could benefit from consistent prefix read. And for the purposes of our example, we will reuse the example which we in details covered in previous video. And here I'll show it just very briefly. So the idea that we are considering enterprise configuration management system where we have some complex transition period which is controlled by those feature flags. And in this example, we have a website which has some pages and main page with references to those pages. And we want to add the page number 3 and the reference to it. And we want to control it with two separate feature flags. One should switch page 3 and another should include the reference to page 3. And due to reasons of our transition plan, we want to do it separately. But we want to be sure that on all followers, on all clients, those flags are switched on in exactly the same order as they were switched on the leader by admin. So first we should switch on page generation, like in this picture, without switching this page reference showing. And then we should switch on the showing the reference. And the opposite situation is prohibited. And because admin switched the flags in this specific order, on leader node we could not have this situation. And basically consistent prefix says us that we will never have this situation on any follower. So basically here are allowed transitions, and we see that on every read from follower we could see one of the following states. Both flags are off, one is off and one is on, and it's important that there could be only one combination of off and on, and it will correspond to exact combination which existed on leader, so it's correct combination for us, or when they both are on. So this explains how consistent prefix could help us to get consistent state across all followers, not necessarily being very strictly synchronized with each other, but each follower is guaranteed to have state which was observed on leader at some point in time. On each new read we could get one of those possibilities, but all of them would work for us, because it will be either this state when two flags are on and everything is working because we have page reference and the page, so nothing is broken, or we have just one flag is on, or we have two flags off, but we never can have this possibility because it never existed on leader. Now let's cover session guarantees or client-centered consistency models. The idea that they are some guarantees which are built on top of eventually consistent system, which are not very hard to achieve, and they can be achieved even in eventually consistent system just with slight modifications of client behavior. And because of this, they are widely used, and they are useful because with the help of session guarantees, we can get some reasonable behavior predictable on the top of eventually consistent system without performance penalties, such as with stricter consistency models like sequential consistency and linearizability. As we know that on top of any eventually consistent system we can relatively easy implement session guarantees, then we also can achieve them on leader follower replication, which provides at least eventual consistency in any mode of functioning. Of course, if we are not taking into account durability questions and failures and failover. I also recommend to watch my two other videos on this topic. One, it goes over all session guarantees or client-centered consistency models, explains them in details, provides definition, use cases, examples, and so on. And another focuses on implementation of session guarantee. It provides exact algorithms how we can achieve them with version vectors, for example. So we know that we can achieve them using some special algorithms. But here I want to concentrate on not using any special algorithms and still achieving some of them. So let's see which session guarantees we can achieve kind of for free and which we can't in leader follower system and what's required for that. First, let's just very briefly review what session guarantees we know and what are they. So they are all provided here in that first heading row. And the first guarantee is monotonic reads. Monotonic reads basically says that if client reads something, then on the next read it will surely see the state of the system, not in the past, and it will see all that it has already read. Read your writes says that if I, as a client, wrote something to the system, on my next read I'll get it back for sure. Monotonic writes says that as a client, if I made write 1 and on top of it write 2, then any client who would make reads in future, they will see those writes in that specific order. So they will first see write number 1 and secondly write number 2. Not in opposite manner. They are prohibited to see write number 2 without seeing first write number 1. And finally, write follows read. It just means that if as a client I have read some state from the system and then made the write on the top of that state, then any other client who would make reads and who would see my write, this client also guaranteed to see at least that state which I have seen on the moment of the write. And let's see if they can be achieved without any special algorithms and in what cases. In this column, we provide some condition from where we do the reads. Here we do the reads from leader, and with reading from leader, it's very easy because all of the session guarantees, they are just satisfied automatically, because when we write to leader and read from leader, basically the system is not really distributed. We have one node for writes, one for reads, it totally orders them, it guarantees immediate visibility. So basically, reading from leader satisfies all session guarantees, but it has some performance impacts because we can't scale reads. We have to read and write on the leader. Now let's see what happens if we read from followers for each session guarantees. And first, for monotonic reads, it's very easy. If we read from the same synchronous follower, or for that matter, from the same asynchronous follower, then monotonic reads will be automatically satisfied because follower it receives and applies writes one by one. And if we read from the same follower, it's obvious that this follower is just incrementally builds its state. It can't just lose writes which were written. Achieving reading your writes is a bit more tricky, but it's also possible with synchronous follower. If we read from synchronous follower, for example, we made some write on the leader. Because the follower is synchronous, it means that it has replicated the data before leader sends the acknowledgement, and if we immediately read from that synchronous follower, then we get back our write. So read your writes is satisfied, but we just need to remember about one edge case about out of order writes, and we should prohibit them. So once we prohibited out of order writes, then it's guaranteed that in such system read your writes session guarantee is satisfied. But with asynchronous follower, it's still not satisfied even if out of order writes are prohibited, because asynchronous follower it can have replication lag, and if we wrote something to the leader, it's not guaranteed that when we read from asynchronous follower we get it back, because it simply might not get replicated. So accidentally it's possible that it could happen, but it's not guaranteed, and because of this we say no here and possible here. And we say possible because if we configure the system in some specific way, that it will be guaranteed and it will be kind of yes. Monotonic writes also possible with both synchronous and asynchronous followers, because we always make writes to the leader and they are always propagated to followers. And if out of order writes are prohibited, then whoever reads from those followers will get those writes in proper order. And the write follows read guarantee also can be satisfied on both synchronous and asynchronous followers. And the only edge case is when there are out of order writes. But in general, if we read something on the follower, it means that it must be already present on the leader, because all writes happen there. And it means that if out of order writes are prohibited, then leader will replicate it to followers, and followers will obviously see the state which we have seen when making the write. So from this table we can make a conclusion that we can achieve all session guarantees reading from leader or synchronous follower or even asynchronous follower. And the only exception is we can't guarantee read your writes when reading from asynchronous followers, but all other guarantees are achievable with special configuration of the system. Now let's review causal consistency. The idea of causal consistency is to detect events which depend on each other, which have happens before relationships. And when we can say that this event definitely happened before this event, and establish partial order between those events. Partial means that some items are ordered and some are not ordered. And items which are not ordered, they are just called concurrent, and we don't know anything about their mutual order. And items which belong to this partial order, which corresponds to happens before order, they are guaranteed to be delivered and be visible by all clients, followers, in the order which is defined by this partial happens before order. It's known and it's written and shown in multiple articles that causal consistency can be just implemented as a combination of those session guarantees. monotonic reads, monotonic writes, read your writes, and write follows read. We already know that we can implement them on top of eventually consistent system. And for implementation, you could refer to those two videos where it's explained in details. And also, if we always read from the leader, in that case, we will have causal consistency satisfied automatically. And actually, we will have even stronger consistency, but we can say that causal consistency will be also satisfied, though in reality it will be much stricter. And the example which is usually given will be social media platform with posts which user can post and comments which users can make below those posts. And it's obvious here that posts of different users made in their timelines, it's not very important what order between them. Even if they are shown out of order, it's not a problem. But if we have, for example, post and a comment below this post, then their order is important, because if someone would see the comment but will not see the post, then it will be confusing and it will be not intuitive and it will be just a bug. And the same situation if there is a post and two replies one after another, and those replies must be seen in the specific order. In this example, we have leader follower system. We have two users, Alice and Bob. Everything that belongs to Alice is depicted as yellow, so there are some posts, comments, and everything that belongs to Bob is purple. So there are posts and comments made by Bob. Because we want to scale reads, distribute them over followers, we will assume that Alice will always read from asynchronous follower 1 and Bob will always read from asynchronous follower 2. Obviously, they write to the single leader node because of the definition of leader follower system where all writes go to leader. And then those writes are just replicated to followers. The idea here that this happens before order, it's shown with those arrows. So basically we see that comment 1, it depends on post by Alice, comment 2 depends on comment 1 and post by Alice, and so on. So basically those arrows, they show us the partial order, which is important to preserve when reading. And for example, there is no arrow between comment 1 by Bob on Alice posts and comment 1 by Alice on Bob's post. And those two comments, they are considered to be concurrent and their order is not important for us. We might ask, why couldn't we just have total order and order all of them explicitly? Well, we could do that, but we don't need it. And when we order something, it's always performance overhead. And less requirements about the order we have, the better performance will our system have. So causal consistency would ensure that all those posts, when it's needed, they are visible in proper order, and when it's not needed, we just don't care about it and they can happen in any order.